Hi, everyone. My name is Andrew, and thank you for listening to this talk. But first and foremost, thank you to the organizers of this new and fascinating kind of conference. I really look forward to seeing all the talks and talking with everyone. Today, I'm going to talk about filling collections of multicurves and volumes. So there'll be lots of three manifolds at play. This is joint work with Tommaso Cremesci and Andres Rodriguez-Migueles. In fact, Andres is also speaking at this conference, so maybe also check out his talk. It's on similar subject matter with a bit of a larger overview of the subject. So what we're going to focus on today is sort of starting with the surface, standard orientable smooth surface of negative Euler characteristic, and we're going to look at its projectivized tangent bundle, which is going to be with the three manifold that kind of plays a role here. And the reason for the projectivized tangent bundle, so the unit tangent bundle, is just for orientation purposes. And what we're going to do is we're going to start with a filling collection of closed curves in minimal position on the surface. So in this particular case, we took two simple curves. It could just be one curve that is filling, not too important at this time. And what we're going to be interested in is going to bring them up into the three manifold, into the projective tangent bundle. And the natural way to do this is to just take the collection of tangents. So we're just going to think of this as a link realized by the tangent lines to kappa upstairs in the projective tangent bundle. So something like this. And by the way, there's many different lifts you could take, but this is sort of a nice canonical one. And the question we want to study really is what does the manifold M sub kappa look like, where we take the projective tangent bundle, and what we really do is just drill regular neighborhoods of these lifts. This is a very natural thing to do in three manifold topology. You have a link, you want to drill it, and you want to understand the manifold that is there. And a wonderful result about this is by Fulton and Hasselblad that shows that it's actually hyperbolic. And this hyperbolic really comes down to this filling condition here. If they're not filling, there's very naturally easy to see that it's not going to be hyperbolic manifold, but when they are, it in fact always is. And if you don't remember what it means to be hyperbolic for this talk, really all that matters is that this smooth manifold admits a finite volume adiametric of constant sectional curvature -1. The finite volume is therefore also important because now we have a volume. And a wonderful result called the Moss-Prasad rigidity theorem tells us that this volume is actually an invariant in the sense that this metric is unique up to isometry. There's no other metrics. There's no deformation space of metrics on M sub kappa. So in particular, we now have this number, which is the volume, and it's completely related to topology of S in kappa. And our goal will be to really understand this relationship and try to see what happens. And one perspective I want to sort of keep in mind throughout this is we really want to think of kappa as a link diagram of kappa hats. So, the picture downstairs is a diagram of what's going on upstairs. And the fact that we're taking this canonical lift is sort of a choice of how to resolve these crossings, right? And that's what the tangent bundle structure is telling us. So what is known in this question? And this is a fairly recent sort of question. It was proposed, I think, 2015, first time I've heard of it. And the first answer comes from 2017. And it says, okay, well, what about the hyperbolic length of kappa? And it says that if you pick a hyperbolic metric x on S, then there exists a constant depending on that metric, such that the volume is linear in the length of the collection of curves kappa. So for any kappa. So the constant depends on the surface, on the metric, but the choice of curves doesn't matter. You get an upper bound. So I wrote it here as the volume of the length is less than this constant. Now, how does this result work? Well, what they come up with is to look at your surface and, if necessary, add some punctures, and then put it in this really symmetric position. And so you now have this, your collection of filling curves on here, living somewhere here, maybe running around. And what you're going to do is you're going to actually add in all of the symmetric copies of those curves under this rotation that you can see here. So just add in all of the copies of your curves under all the rotations. So you've added curves, you've possibly added punctures. There's also this red curve. And now you're going to look at the quotient downstairs, and the quotient downstairs looks something like this. And now you're going to have your possibly, let me just draw them as red, and it doesn't quite matter, green curves that are still filling downstairs. And then you're going to further quotient this down to an orbifold. You're going to quotient it down to the modular surface. So this is the one cusp with two cone points. And now curves on on the modular surface are really nicely behaved in terms of how they can be encoded, and their length is related to lots of other geometric properties. And further, the tangent bundle of the unit tangent bundle of the modular surface can be realized as the complement of the trefoil. And so you can actually think of this in S3, complement of the trefoil in S3. So you can think of all of these things as actually links in S3. And so you have some interesting pictures and things you can work on hand. But notice here, you're adding stuff to get an upper bound. Similarly, kind of following this diagrammatic concept, Tommaso and Andres were able to show recently that we can also do this with self-intersection number. So here I kappa kappa is the self-intersection number of kappa. And the way this works is very similar to what you do in sort of diagrams of links in S3, where you really just sort of add you add more link components, and then you build an ideal triangulation of your manifold. And so here, this is essentially what you do. For every self-intersection, you're able to add some, drill some more curves from the manifold, and you can actually get this upper bound. And this upper bound actually works for any lift. It doesn't have to be the canonical tangent lift. Now, the problem with all of these is, of course, that we're adding stuff. If we really want to understand a lower bound, then we're kind of in trouble because we keep adding punctures and we keep adding curves. And if you're familiar with three-manifold topology, when you drill stuff, when you drill curves, in a three-manifold, you're increasing the volume, if you're familiar, I guess, with the hyperbolic three-manifold geometry. And so this makes lower bounds a little bit difficult. The first lower bound that is kind of universal came from Andres in 2017, and it says that if you now take some simple multicurve eta on S, and you consider cutting S along that, and you're interested in what kind of isotopic classes of kappa arcs remain. So kappa could be some quite interesting looking curve on your surface, but it might have some sort of fairly innocuous isotopic classes of arcs that live inside of your pants decomposition. So maybe kappa does something like this, right? And so you actually don't get too many complicated arcs maybe, but so you just look at the isotopic classes of arcs that you do get, and the number of those gives you a lower bound. Now, this is a pretty nice lower bound, especially if you have lots of these different isotopic classes of arcs, right? But the problem is you're not going to have this if kappa is composed of simple closed curves, right? So this works very well if you have lots of self-intersections and you're one closed curve and you have a lot of different interesting homotopic classes of arcs developing. But if you're simple, so if you're filling a collection of simple multicurves, then really all you get are the standard simple arcs that you can have in a pair of pants or on a surface with boundary. There aren't that many of them. There's a finite number, and so this lower bound is actually constant in that setting. And to alleviate that, well, we really wanted to understand what happens in that particular scenario. So the goal for this talk is to say, what are the asymptotic upper and lower bounds when kappa is a collection of simple multicurves? So when this lower bound fails, right, what can we do? When this lower bound doesn't grow in any way besides a lower bounded constant, what can we say? Can we actually say things go to infinity, and what kind of examples can we get? So the main result of our paper is that if we take just two pairs of simple multicurves and they're filling jointly, then we can actually give you a quasi-isometric bound on the volume. So here the volume will be related to this distance in this infimum of this distance in what's called the Pants graph, and also the Weil-Peterson distance between strata. So let me define all of those things. So first, let me talk about what this little symbol is. That is a quasi-isometry. And what I mean by quasi-isometry is just a relationship between two functions, and it says that they're sort of linearly related. So we say that f of t is at least 1 over a times g of t minus b, and at most a g of t plus b for some constants. And these constants in our theorem only depend on the topology of S, nothing else. So that's sort of a nice relationship. Now let's talk about the Pants graph first. So if you recall, the Pants graph is the collection of all Pants decompositions where an edge corresponds to an elementary flip. So here's a Pants decomposition on the right here, and an elementary flip is saying take one of these curves. So let's say this guy right here, and consider a curve that intersects it exactly once. So for example, the standard guy right here, right? And there's actually infinite choices for curves that intersect it exactly once. You can think of all sort of the Dane twists of the blue curve under the yellow curve, right? And that gives you a new Pants decomposition. And in the Pants graph, that is just one edge of length 1. And so if you have two Pants decomposition, there's naturally a minimal length path between them, and that gives you this distance in the Pants graph. Now, what do we mean by P alpha and P beta in our theorem? So what we want to say there is if we have some curve or some multi-curve, let's say that gamma is composed of these two pieces here, right? We can complete gamma to a Pants decomposition. So in particular, the choice of all three of these is some completion of gamma to a Pants decomposition of the surface. And there's many choices to do this. And our theorem says that if we look at any completion of alpha, any completion of beta, look at the distance and then take the infimum of that distance over all possible completion, that value is quasi-isometric to the volume. Now that's a bit of an odd metric, and it's kind of hard to understand. So one way to sort of make it a little more geometric is to look at this Weil-Petersen scenario. Now, what do we mean by this right-hand side? So many of you might not be familiar with Weil-Petersen metric, but let me just sort of say a few words about it. So the ball down here is representing Teichmuller space, which is the space of all, let's say, conformal structures on S, if you want hyperbolic metrics as well, marked. And a Weil-Petersen metric is an incomplete negatively curved Kähler metric on this space, and it's very natural and quite interesting. And the nice thing about it being incomplete is that you can take a metric completion of it and study that. And essentially, that is where T alpha and T beta live. They actually live on the boundary of Teichmuller space with this metric completion. And essentially, what they correspond to are usually what called strata, where you take the curve alpha and you just pinch it on your surface. So if you pinched, if this whole thing up here was, if this guy was alpha, let's just say, yeah, let's just pick one, and you imagine pinching that curve, you're going to get a surface with a node, right, sort of a cusp, and now it has its own space, Teichmuller space, and essentially that's the Teichmuller space you're attaching over here. Now, what our theorem says is that the distance, which happens to be finite between these, and it was of course known to be finite, between these strata for pinching alpha and pinching beta, is exactly quasi-isometric to the volume of the manifold in question. So that is sort of our main result. And now we can take it and do some sort of do some applications to sort of just studying the asymptotics of this volume. So the first things you might want to ask is, okay, well, what happens if I take a pseudo-Nassau? Well, if you take a pseudo-Nassau and you look at two curves, let's say alpha and beta, they don't have to be filling, but once you take a high power of phi and apply to one of them, they're going to be a filling pair. And in that question, you're going to look at the volume over the n times the translation distance. So this is the Weil-Petersen translation distance on Teichmuller space, or if you want on the Pants complex. And the ratio of those two is going to be a constant, or it's going to be quasi-symmetric to a constant, sort of asymptotically constant. This constant is, of course, going to depend on alpha and beta, but still, you know, we can see the rate of growth of this volume, and we can see that it indeed has to grow. So that's sort of a nice first example. Another thing you could look at is in the special cases. And so in the special case of the once punctured torus and the four punctured sphere, what we can do is actually give you some nicer bounds. So if you think of a sequence of filling pairs of simple closed curves, what you're going to get is that the volume over the log of the self-intersection number, and remember we had an upper bound in terms of the intersection number, here we have the log of the self-intersection number, the lim sub of that is going to be less than some constant. And if you want to look at the hyperbolic length, we're also going to see that the volume over the log of the hyperbolic length is going to be less than a constant. And both of these are going to be possible to attain. So you can actually make these, you know, get non-zero sequences here. And so this behavior is quite different than the upper bounds we sort of saw, in the sense that instead of thinking that it's actually the length, this looks like to behave more like the log length and log intersection number. So what we actually suspect is that log x is asymptotically implemented for what are called stratified canonical lifts, and we'll define that a little bit later. And it sort of sets up a dichotomy because for non-simple closed curves, this is not true. So if we look at non-simple curves, kappa, and we look at their canonical lifts, Andres has given some examples where the volume grows like log x, length x over log x, so faster than this. So there's a transition from simple multicurves to filling collections of simple multicurves to filling closed curves, period. There's something different having when you have a closed curve that has sort of self-intersection. Even more so, you might want to consider what happens for arbitrary lifts. Like I can pick how I resolve the intersections. I'm not going to use this tangent bundle structure at all. And it turns out that you can do much worse. So Andres gives volumes that grow like length of the curves, and you know, the lower bound is also sort of the upper bound is also sort of different. We know that we have an upper bound of intersection number from Tomaso's and Anders's paper. So in particular, we have this lower bound. Well, we have sequences that grow at least as fast as the length, and at most as the length squared. So arbitrary lifts are also quite weird. So, you know, the picture here is that there's still a lot to study, especially in the case where the curves have self-intersection. But in the case where curves are, you know, simple collections of some multicurves, we have a decent handling on this picture, at least for pairs. Now, let me tell you how this idea works and how we actually got to prove this. And I'm going to just give you sort of an example. So the idea is, first, if you have a surface and you have two curves, is sort of in a controlled way, add some punctures to make the projective tangent bundle trivial. So here's a nice little picture. It's a sort of a slit construction. If you've never seen it, it's very, very nice. So you can see that the two surfaces here, the two little rectangle squares on the left-hand side, if you look at the side pairings, you just get tori. What we're doing is we're cutting a slit so that this black arc is identified with the black arc on this other torus, and the green arc in the other way. So what happens is if a curve goes along here, it comes out on the other torus. And you can actually see the genus 2 surface that you get from this picture. Now, the curves here are filling, but we really want to sort of can think about these sort of cone points from the slits as possibly going to be punctures. Now, the reason for this is in the trivial bundle, we can sort of find nice surfaces to separate our two lifts. And if you think about here, there's sort of two very natural surfaces up in the projective tangent bundle of S minus those punctures. That is the horizontal tangent field and the vertical line field, right? So there's the horizontal line field that carries the pink curve, and then there's the vertical line field that carries the blue curve. And the nice thing about that is that you can now have, if you just take a slight rotation of the horizontal field, it now sits between the two lifts. And now you have a surface embedded inside of your 3 manifold, and you can do some work with that. And that's essentially what we do. So here, if you think about S1 and S2 as being sort of the vertical plus an epsilon rotation and the horizontal plus an epsilon rotation fields, they separate the lift kappa hat into little chunks. And what we do is we look at the cover. So M sub I to M sub kappa corresponding to the fundamental groups of these surfaces. And you get manifolds that are actually sort of limits of, if you know what quasi-Fuchsian manifolds are, in this case where sort of these, your cusps do lift to actual short curves, and so you're looking at a manifold of this type. So these guys are sort of well-ish understood manifolds, and there are pieces of them that we can understand and see how they project isometrically into M kappa. And so this comes down to sort of the wonderful work of Brock, which tells you how the volume of this nice little chunk that kind of maps into M kappa in a nice way. It's not entirely true, but there's some work to be done there. But you know, this what's called the convex core of, oh, sorry, that's supposed to be M sub I. This convex core of M sub I maps nicely, and that volume is actually quite well related to the Pantz distance. So that is sort of the attack vector. And the one last thing that we have to do with this attack vector is kind of figure out how do we undo the impact of adding these punctures. So the machinery is start with curves, add punctures so you have these nice separation surfaces, look at the covers, look at the sort of compact convex chunks in there, and the volumes of those are really giving you good estimates on the volume of the manifold M kappa. And then figure out some topological arguments to say, well, there's a way of sort of relieving this added puncture business. So that's how we got to the motivating example. Now, the full generality of our result is kind of dealing with the reverse picture than what I showed you in the very beginning. I went from curves to links upstairs. The more generality picture is you start with a link and you go down. So let's maybe quickly go over that. So the general picture is instead of starting with curves on a surface, we start with a ciphered fiber space over S. So very similar to projected tangent bundle. And then we're going to consider a link that is fiber transverse with a projection that is in minimal position. So this is where, again, kappa, thinking of kappa as this weak link diagram is very helpful. So we have this link upstairs in N, and we have here our surface S, and we have our curves kappa here. And what we really want to do is replicate the behavior that we did there. We want to find these separating surfaces. And so one thing, just to, again, to say that result of Tommaso and Andres is about hyperbolicity in this question. And they do indeed show that hyperbolicity is equivalent to being filling and also being acylindrical, but that's a minor detail. And they also show this holds for orbifolds. So now going back to what we really want to do is sort of replicate this separation business. And what we call this is we call this a stratification. And the stratification is sort of a disjoint collection of properly embedded surfaces where chunks of our link live. So think of those like horizontal and vertical pieces from earlier. And the way you really want to think about it is here's, let's say, this is sort of a small diagram of S. Here's a diagram of N. And what we're going to do is we're going to really think about, our curve as like a couple of dots. So this is a very algebraic geometric picture. And we're going to think about these lifts up here. And what we want is surfaces where one chunk lives and another chunk lives. So this is S1 and this is S2. And so the stratification is something where that's possible. There are going to be lifts that don't have this property, where you sort of wind around a bunch around the fiber and you intersect any possible way of the surfaces behaving nicely. And you should really think about this sort of picture very much like those sort of line fields on a surface. The flat picture is very, very useful. Now, once you have sort of these properly embedded surfaces, you can just order them cyclically around the fiber. And we call a such choice of surfaces in the link is a stratifiable link. And we call this collection H a stratification. And the right picture is really, really that you're telling us how do you want to resolve crossings on your surface. So what can we say in this particular setting? So for stratified links, so what we can do is that the picture becomes a little nicer. So the hyperbolic link upstairs, so this link that we started with, split into these little pieces. We now have these surfaces, but because we're in a cipher fiber space, these surfaces actually are horizontal. So they're transverse to the fiber, and which tells you they're actually fiber-wise isotopic because they're disjoint. And so we can really think about just cutting everything open. So, we had this picture where, I really drew this S down here with our little curves here and here. And the perspective we want to have is two curves moving up there, down there. And we really want to think about, okay, well, we can cut along the stratification surfaces. Now we get a nice little interval bundle, and there's some gluing map between them, and we have a nice downward projection. So we really can just say everything lives on our surface S1. So we can really just project everything down. And so the stratification surfaces are just really nice behavior that we want to have. And there's some gluing map that, and once you cut along these, there's some gluing map that sort of corresponds to going through S1. I call it psi sub H. And so our main result is that is that doing this gluing gives you some sum of Pans distances. And so the particular formulation is a little bit complicated, but essentially you're saying, look at the volumes of the manifolds in question. So we drill out our link, and what we're going to look at, the Pans distances between sort of the projections of our sort of completed Pans decompositions. So we have these projections of our sublinks onto the first surface, and we're going to look at the sum of all of those, and we take the infimum over all sort of completions. It's very identical to that same picture. And so you have sort of a lot more control in a more general setting. And so you can apply this, for example, to, collections of simple curves on a torus, let's say. In that case, you can just stratify it, and you have this infimum of a sum. So the general picture is a little convoluted, but it does provide us with sort of a stepping stone. And so the point of the construction is, again, to sort of, we start with our curves, we add punctures, we get a stratification sometimes, and the reason why we have pairs in the beginning is actually that's when we know that we can always get a stratification, and then we apply this theorem. Now, to conclude, let's look at some open questions. Now, first things we just talked about was a lot of sort of simple multicurves. What happens if what happens if we just have a closed geodesic? Like, what if something has self-intersection? What is the right measure in the combinatorial sense of this volume? So we know upper bounds, but we don't really have the lower bounds. And we know that length and self-intersection aren't quite good enough. We have examples of curves where the length goes to infinity, but the volume stays bounded. And we also have self-intersection staying, going to infinity, but volume staying bounded. The other question is, what about a random geodesic? So what happens if you take a random closed curve? What does that look like? Another question that we don't really understand is, what kind of cusp shapes do you get? So every three-manifold with a hyperbolic structure has some cusp shapes, and the very kind of common question is, what shapes can you get? Different links, different knots, and things like this. So, and it's probably going to be quite different from, in the simple closed curve case, to the curves with the non-simple case where you have self-intersections. And finally, we really understand exactly that behavior. So recall this lower bound that Andres had about the isotopy classes when you cut the surface open along some multicurve. And for simple closed curves, we have this constant lower bound. And what that really tells you is that because we know the volume grows, we know we can make examples with the volume grows, so it tells you that the volume is not coming from these isotopy classes. Right, the volume has to sort of come from inside of the manifold in the thick part, in the interior. So not near at infinity, not near the cusps. But the behavior of non-simple closed curves sort of seems to indicate that really the volume is coming from these isotopic classes. It is coming from that particular case, from actually just very large cusps. And big question is that really the case? We don't know, and that kind of relates to the cusp shape question. So that was it. Thank you all for listening, and I look forward to hearing all the other talks at this conference. Thank you so much.